Yes, I'm starting the recording for day 2 class today. We have a little bit left in our worksheet, thermal worksheet, gas law worksheet, so which we are going to cover after a while. I just feel like starting a new chapter today because it's been long since that I did not teach a new chapter. So yes, today we're gonna start chapter number 4 in my preferable division of the syllabus, A2 syllabus, say A2 syllabus. Which is going to be capacitors and electric field. To be honest, I'm going to be teaching these two topics in the other way around. So I'm going to first teach you the electric field part, and then I'm going to go for the capacitors. I don't know why the name shows up like that. It's just that. And also, okay, let's just jump in. Couple of things that I would like you to remember. What you should remember from your O-level syllabus is that what you have learned about electric fields. In your O-level syllabus, there was this much involved in your electric field that you have learned. Electric field strength is the force experienced by, so not O level, in your S level, electric field strength is the force experienced by a unit charge, or electric field strength E equals to F by Q. Do you guys remember that equation?
Yes, sir.
E equals to F by Q. So this is the definitive equation, or definitive equation for the electric field strength. That's one thing. And then we have also come to, we also knew that electric field strength can also be expressed. Then we have also knew that electric field strength can also be expressed for a parallel electric field, or where the two plates producing electric field are parallel to each other. For those cases, we can also express the electric field strength as V by D, voltage across the two plates divided by the distance between the two plates, which we also have over here. We're going to use those information over here as well. But that's all you have learned in your AS level. Additional to that, you have also done some mathematical calculation where a combination of electric field, charge particle moving through an electric field, and a bit of a positron motion was somewhat involved with each other. So we have found out that how the particles are going to move around whenever a particle is relevant in that manner. So that was the part that we have covered in our AS syllabus, which is actually really small compared to what electric field is all about. We're going to see a little bit additional version of this thing. One thing that I would like to recall, that many of the parts which we are going to see over here are going to be similar to the discussion of gravitational or Newton's gravitational law that we have seen in our first chapter. So in many cases, I'm going to pull reference or relevance of those chapters. If you need me to remind you of those things, ask it so. Or if you don't, we're going to move on forward. So they're going to pop up every once in a while in my discussion. And once again, since we are doing a discussion class, I highly appreciate if you have any question, raise your hand and I'll take your question in due time so that you can tell me your question. You can pause me or stop me immediately if you need me to slow down or if you need me to repeat, which is perfectly immediately stoppable, no big deal. All of you have your, you can unmute yourself. So let's start. First thing first is Coulomb's law. Coulomb's law is basically the law that defines the force between two charged particles. It's very similar to the Newton's gravitational law. I'm sorry?
So like apni ki on korchen eta, I guess screen dekhte partechen na keno?
It's fine on my end, sir.
I have started the screen sharing. Everyone is having a look at it. I believe it's visible for all of you, right? It's supposed to be visible.
Yes, sir.
Yes, sir.
No problem.
Yeah,
Yes, sir.
ঝামেলা হলে লগ আউট করে আবার লগ ইন করো মানে রুম থেকে see if that solves. So Coulomb's law is a basic version of the Newton's law. So the key point that we're showing over here, that if we have two charged particles, Q1 and Q2, magnitude, signs, they are not labeled over here because this is a generalized version. If the distance between the center of those two spherical objects is r, I mean, the reason we have used, why do we use spherical shape and why the distances are labeled from center to center, I'm going to get into that part in a bit. This is an important aspect that you have to understand as well. But let's assume we have two charged particles. I mean, whenever I use the term charged particle, I mean that all of this charge is centered at the center, concentrated at the center. Or if it's a charged sphere, it's basically the charges are spread out on the surface. Why charges spread out on the surface? সেগুলো আমি বলবো, আস্তে আস্তে বলবো. Let's say we have two charged objects, Q1 and Q2, having these are their charge values, and they are separated at r distance from each other. Then the electrostatic attraction or repulsion force between those two charged particles are going to be given by these two expressions. This is Coulomb's law. Coulomb's law is finished up to here. That force, electrostatic force, is proportional to the product of the charge values is inversely proportional to the square of the in-between distance. Very much similar to gravitational law. If we combine these two proportionality, we get this one. To make this proportionality into an equation, we bring about a proportionality constant, which is K. The basic equation over here is the actual expression for Coulomb's law. Now, I'm going to take this into my MS Paint. Okay. So the basic expression of Coulomb's law practically finishes up over here. Now, this part of the equation is basically what we are going to use for our mathematical operation for our working procedure. The thing that I need to understand that this K is not an universal constant like gravitational, like G. This K is a medium dependent constant. What do I mean by this medium dependent constant? What I mean is that if we have two charged particles of equal magnitude, let's say for the sake of example, let's say we have two charged particles, each with charge value of 10 Coulomb, plus or minus whatever. If they are like charges, they're going to repel. If they are opposite charges, they're going to attract. So be it that. Let's say we have two charged particles placed at same distance, and we're going to vary the medium in between those two charged particles. If you place those two charged particles in vacuum, they are going to apply a certain value of force across each other, onto each other. If you place another medium, let's say if you place water in between them, they're going to have another value of force. If you place another medium, let's say glycerin or oil or mercury, or if you place some electrolytic solution in between those two charged particles, depending upon the medium that is located in between those two charged particles, that force of attraction or repulsion of electrostatic force are going to be varied. This is where the K comes in, which is actually a medium dependent constant. For our purpose, for simplicity's sake, your syllabus is designed to work all of our mathematical calculation using the vacuum, which means we are going to assume all the charged particles that we're going to use for our mathematical calculations, they're going to be located inside a vacuum chamber. So there's not going to be any medium present in between. As a result, that K is written in this format, 1/4 pi epsilon naught. This is the mathematical equivalence of this equation, where epsilon naught, this is the symbol that is that the name of the symbol is permittivity of free space. Permittivity of free space is basically, this word means that how much does the free space allow electric force to work through itself. That's what we mean by permittivity. For those of you who have biology, or you have had biology, and for those of you who ever have come across the idea of osmosis, do you guys know this word osmosis?
Yes, sir.
Yes, sir.
Yes, sir.
For those who don't know this thing, let me tell you this thing. Osmosis is basically the process where if two solutions are separated by a semi-permeable membrane, then materials, it can be solvent, it can be solute, materials, we are going to try to move from their high concentration location to their lower concentration location. That's how materials are going to move. Now, if you have an impermeable membrane, for example,
Sir, it's only water, only for water.
now osmosis, I'm not defining osmosis right now. I'm just trying to give you a basic idea about how the particle movement happens. So osmosis, so that's the basic idea of diffusion. Diffusion means that particles are going to try to spread out from the high concentration region to the low concentration region, which can be happening by Brownian motion, and there can be other forces involved. I'm not getting into the details of that, but the basic idea of osmosis is that osmosis, we use the term osmosis for how much solvent is going to move across that material. Solvent or solute?
Solvent, sir.
Okay, yeah, how much solvent can transfer between these two material, and having a semi-permeable membrane means that it is going to allow the atoms or molecules or ions to pass across itself selectively. Not all of it can enter. For example, a cell wall can be considered to be an impermeable wall, which is applicable for plant cells. Whereas a cell membrane is a semi-permeable membrane. It can choose by its own construction and its chemical components that what are the materials I want to get into my cell for my purpose, and what are the things that I do not want to allow. So based upon that, it gathers nutrients, and eventually it can feed its own body and all the stuff that is inside the cell, and it can work with that. So the reason I'm bringing up the idea of osmosis in this symbol, in this case, because I wanted to try to give you the idea that electrical force is a medium dependent force, unlike gravitational force. Gravitational force is not medium dependent. What I'm trying to say, If you have two 10 kg objects placed at 1 meter distance from each other, whether the in-between medium is vacuum, in-between medium is water, in-between medium is mercury, in-between medium is whatever, solid or some solid material, sand or something like that, the gravitational force between each other due to their own masses will always have the exact same value, irrespective of the medium in between them. That's for gravitational force. But for electrical force, it is going to be highly dependent on how much, what is the medium that is present in between those two medium. If you wonder why does this work, let me give a very simple idea. It's because of the idea of induction. It's because of the idea of induction. Because electrical forces, electric field lines can produce inductions, which means what I'm trying to mean is that, let's say, if this is these are the two objects. Let's say this is the two objects. So I'm going to copy this up and take it a bit elsewhere. So let's say here is the thing. If I have vacuum between them, the electric field lines between these two, let's assume for the sake of simplicity, let's say this is a positive charge, this is a negative charge, and for this timing, let's assume they are equal charges. So in this case, the electric field lines are going to travel from positive to negative. We all know this thing, right? Coming perpendicular out of the surface, getting perpendicular into the surface. You know how these field lines work, and this is going to be like this. So I can draw a bit of discontinuous line just to represent that these lines are going to be present, but we're not showing those lines because we have space constriction. So this is how this is going to work out, and similarly over here as well. So so if it's a vacuum, it can be this way. Vacuum is basically a non-conducting material, so there's nothing to work with. If you have, let's say, another non-conducting material, let's say if you place a glass over here, now glass is going to allow electric field lines to work through itself in a different manner compared to how much vacuum allows. If that's a bit difficult idea for you to understand, let me show you another example. Other than having these two particles directly located in vacuum, let's say if we bring about a piece of another metal block over here, let's say if we bring about one metal block right over here, let's say let's say this is a metal block, and I want to fill this up with black. Can I fill this up with black? I cannot fill this up with black. Okay, let me try just to do it by shading. So, oh no. Okay, so let's say this is a metal piece. Okay, this is a solid metal piece. So whenever you're going to place these two charged particles on the two sides of the metal piece, induction will happen. As a result, the left side of this metal piece is going to become what kind of charge? What charge will be available here?
Negative.
This side should become slightly negative. This side side should become equally positive. Electrons cannot leave or enter into the situation, but because of the induction forces, the electrons are going to separate out, so that one part is going to have higher positive charge concentration, the other part is going to have higher negative charge concentration. We cannot say this metal block is currently charged because the total number of protons and electrons are exactly equal, but we can say the object is showing a charge behavior which is temporary, and this is called induction. You know what I'm talking about. So in this case, what's going to happen? These field lines for this scenario is not going to be similar like this one. In this case, the field lines are going to get concentrated over here like that, from positive to negative, and then field lines are going to come out over here. So you're going to have a more concentrated field line situation compared to this case. The amount of separation that the field lines had over here, you're going to have a much less concentration over here, because this metal piece are going to allow those electric field lines to become more closer to each other. Or in other words, I can say this metal medium can allow the electric force to work with much more effectiveness. That's one way to put that. Now, because I am using this, so this is exactly why electric forces will be a medium dependent force. So that's why we are having this thing. Where does this 1/4 pi comes from, which I am not going to discuss in detail? This actually comes from the idea of three-dimensional angle. Do you guys understand what a three-dimensional angle is? Have you guys ever heard about this?
No, sir.
For those who haven't, let me just show you an example what a three-dimensional angle is.
The lines intersect at a point.
Not essentially lines. Images. Have a look. A three-dimensional angle is something like this. So let's say you have a sphere. If you take out a conical shape out of a sphere, this is what a three-dimensional angle is like. It doesn't have to be conical. It doesn't have to be conical. It can be a pyramidal as well. For example, this is an example of a pyramidal angle. So this is a three-dimensional angle. Two-dimensional angle is made up of two things. Three-dimensional angle is made up of four border lines or a continuous surface. So I cannot explain this properly in words, but you do get the idea of what is happening here, right? The basic difference of a 2D angle and a 3D angle. Do you understand this difference just by looking at this?
Yes, sir.
Yes, sir.
In the calculation of this three-dimensional angle, somewhere this 4 pi pops in. If I give you a small bit of idea, what is the total surface area of a sphere? What is the total surface area of a sphere?
4 pi r square.
4 pi r square. Do you know this thing?
Yes, sir.
So ওই 4 pi r square 4 pi টাকে কোনোভাবে ইনভলভ করে আমাদের এখানে একটা 1/4 pi আসছে। এটা কিভাবে আসছে সেটার এক্সপ্লেনেশনে আমি তোমাদেরকে যাচ্ছি না। If you want, I can give you the necessary document and I can direct you to the internet pages, or you can Google it up in yourself. It's pretty easy to find. You can look it up, how did this came into existence, but that's not a part of our syllabus, so I'm not getting deep into that. So what I need you to understand that K can be written in this shape, 1/4 pi epsilon naught, where the epsilon naught represents the permittivity of free space, and this is the variable that we're going to work with. So this is the ultimate final equation for our purpose. In our formula sheet, both the value of K and epsilon naught would be given to us. So you can use either of them for your calculation. I personally prefer to use the rounded off value of K. Let me just show you what I mean by that. Pretty fast. Let's say if we choose any random year's quotient, turn up any of the question paper. Have a look. AJ. Permittivity of free space. Epsilon naught has a value of this much. This is farad per meter. Farad ki jinish eta pore boltechi. And if you want to get the total value, 1/4 pi epsilon, that is 8.91019. I prefer to use this number so that I have to press less calculator numbers. So this is the entire value of the whole fraction. This is the exclusive value of the permittivity of free space. There is another variable which is permeability of free space. This is applicable for magnetic forces. There are two different words. Permittivity is exclusively used for elliptical scenarios. Permeability is used for magnetic scenarios, which we're going to see in our next chapter, which is electromagnetism. Pretty big chapter. And before I start electromagnetism chapter, I'm going to stop admission to your batch because that's how I do. That's how I roll. So yeah. So permittivity of free space is going to work. Achha, there is this new kid that is supposed to do a start class today with us from Green Herald. Are you with us in the class? কি যেন নাম ছিল? Hello? I just remember. Please just give me a moment. She was supposed to join today's class, but is she doing today's class?
Sir, I'm a new student, but I'm SRU থেকে Scholastica থেকে.
Or did I talk to you?
Yes, sir. I'm Green Herald, not Scholastica.
Sorry. I messed up. You are this kid. কই গেল? এই যে এটা, মাজবেন নূর.
Yes, sir.
But you look like Noshin.
এটা অন্য অ্যাকাউন্ট থেকে জয়েন করে ফেলেছি।
আচ্ছা সমস্যা নাই। ক্লাস বুঝা যাচ্ছে?
Yes, sir.
If you have any question, raise your
No,
hand.
sir, not yet.
Beautiful. I just remember that there is some other key supposed to be. So permeability is a similar constant that we use for the case of magnetic forces, whereas permittivity is the constant that we use for elliptical forces. So permeability যখন আমাদের ডিসকাশনের মাঝখানে সিকোয়েন্সিয়ালি আসবে আমরা তখন এটা নিয়ে আলাপ করব, but I just wanted to have a look that these constants will be available to us, so you can use them for your calculation. All right. এখানে গাদাখানি জিনিসপত্র লেখা আছে. I'm going to take questions from you kids, but for those who do not have any question, I want you to read through this part and you can talk to me about this. Okay. I'll take questions. যারা কোশ্চেন করতেছো না এই পার্টটুকু পড়ো. শুভ্র.
স্যার আমি আসলে জিজ্ঞেস করলাম স্যার আপনি যে মিডিয়ামটা বললেন ওটা কি কোনো কন্ডাক্টর হতে পারে, যে কোনো?
এটা কন্ডাক্টর হতে পারে, নন কন্ডাক্টর হতে পারে, মিডিয়াম লেস, ভ্যাকুয়াম হতে পারে. It can be anything. It can be an electrolytic solution, for example.
স্যার ইলেকট্রোলাইটিক সলিউশন হলেও তো কন্ডাক্টর বেসিক্যালি।
ওই তো ওটা বললাম, মানে it can be anything. Anything means anything, literally anything, or it can be nothing as well, vacuum.
আর যদি স্যার ওটা ম্যাগনেটিক ফিল্ড লাইন্স বলতাম তখন ওটা ম্যাগনেট হয়ে যেত অর সামথিং।
ওটা ইলেকট্রোম্যাগনেটিক চ্যাপ্টার আলাদা করে বলবো। আপাতত ম্যাগনেটিজমের মানে ইনফরমেশনটা ডিটেইলস ইনকর্পোরেট করতে যাচ্ছি না আপাতত।
ওকে স্যার।
ওকে সাজিদ।
Sir, K value to the constant, right?
For no, K value to constant na. K is a number which is highly dependent on the medium. For vacuum it is constant. and we are going to use all of our mathematical calculation for vacuum. All of our mathematical,
আমাদের ক্ষেত্রেই বলতেছি, মানে আমাদের তো খালি ভ্যাকুয়ামটাই আছে, আমাদের তো অন্য কোনো ইয়ে নাই, মানে মিডিয়ামটা নাই। সো
that's the part that I would like to highlight. Let me elaborate this. All of your mathematical calculations are designed to work for vacuum. It is quite unlikely that they're going to give you for a different medium. But if they do ask you a question that where the two charge particles placed in a different medium, they're going to give you this number, or they're going to give you this number associated in the question. In that case, you have to cautiously and consciously replace this constant for that medium. যদি তারা চেঞ্জ করে দেয়, ঠিক আছে,
আচ্ছা আচ্ছা,
আইডিয়ালি দিবে না, এবং কোন কিছু বলে না দেওয়া থাকে তার মানে হচ্ছে they are placed in vacuum. Default is vacuum. If anything different is to be done by you, then the question will give you that information. You have to replace the k value appropriately.
আচ্ছা আচ্ছা, বুঝছি।
Okay, Ramisa.
আচ্ছা স্যার, মাঝখানের মিডিয়ামটা যদি কন্ডাক্টর হয় তাহলে তো আপনি যেভাবে বুঝালেন ইন্ডাকশন তো হবে না, সো তাহলে তখন কি হবে?
Well, মাঝখানে মিডিয়ামটা যদি ইলেকট্রিক্যালি কন্ডাক্টিভ হয়, মানে হচ্ছে if let me put it straight out. If the in-between medium allows the electric field lines to pass through them more easily, which means it's a conducting medium, the electric force is going to be stronger. If it is a non-conducting medium, I mean, you might think that, yeah, কি বলে এটার নাম কি জানো, vacuum is a non-conducting medium because vacuum is nothing. How could something be more non-conductive than vacuum? Vacuum এর থেকেও স্ট্রঙ্গার নন কন্ডাক্টিভ হইতে পারে যদি আমি একটা প্রি চার্জ ইনসুলেটর ম্যাটেরিয়ালকে উল্টাভাবে বসাই। সেটা কি জিনিস সেটা আমি পরে বলবো। বাট what I'm trying to tell you over here, what I want you to understand, that the effect of the medium is gonna affect, the presence of the medium is gonna affect the value of your force. It's not gonna be always the same constant. So যদি আমরা একটা কন্ডাক্টর মিডিয়াম দেই, আইডিয়ালি আমাদের ফোর্সের ভ্যালুটা বেশি হবে। এটা আমাদের থিওরিটিক্যালি বুঝতে হবে, বাট ম্যাথমেটিক্যাল ক্যালকুলেশন করার জন্য এটা ইউজুয়ালি আমাদের ইম্পর্টেন্ট না।
আচ্ছা স্যার, বুঝছি।
ওকে, আবিয়াজ।
Sir, I'm slightly confused about the part that electric fields can get differently in different environments.
No. Electric fields are in the same element. The electric fields are always traveling from positive to negative. But for this scenario, the electric fields are really congested, which means represents a stronger electric field, more force. For here, the electric fields are pretty far apart, which means a weaker electric field, less force.
So electric field lines, they're like imaginary lines, right? So they're not physical things.
No.
When we say the permittivity of free space, what is being permitted, sir?
The working of the electric force, or if I answer your question more accurately beyond the scope of the syllabus, is that there are 4 fundamental forces in nature. They work by exchange of 4 fundamental particles. Gravitational force are assumed to work by exchange of gravitons, which are not yet detected. Electromagnetic forces work by the exchange of photons, which are detected. Strong nuclear force usually work by the exchange of, I think, bosons, I'm not sure. And weak nuclear force, I think, work by exchange of neutrinos. I'm not sure as well. But the forces that exist in nature, the basic fundamental 4 forces, they work by exchange of 4 different particles. In this case, to answer your question more accurately, beyond the scope of the syllabus, is that how much those photons, how conveniently those photons can travel from one particle to another particle is basically what the permittivity is all about.
So it's basically how easily the force carrier, in this case, can do the thing.
Beautiful, yes.
Thank you, sir.
Yeah. Fardin.
Sir, the thing is like a vacuum এর বদলে ভাবেন যে আমি একটা মেটাল বসালাম, so like electric field lines are closer হবে, so আমার ফোর্সটা বাড়বে, so ও k এর ভ্যালুটা ডিফারেন্ট হবে যখন মেটাল বসাবো, রাইট?
Yes.
মানে মিডিয়ামটা চেঞ্জ হয়ে যাচ্ছে।
Yes.
That's the thing over here, right?
Yes.
Nothing else.
Nothing else.
Okay. Thank you, sir.
সো এই পার্টটুকু নিয়ে আর কোনো কনফিউশন আছে নাকি? এখানে সব নরমাল কথাবার্তা বলা লেখা আছে। আমি এতক্ষণ যেগুলো বললাম মিডিয়াম রেটে, সেগুলো এখানে লেখা আছে। তারপর বলা আছে হচ্ছে যে লাইক চার্জেস, অপোজিট চার্জেস হলে কি হবে, এগুলো।
স্যার পারমিটিভিটি অফ ফ্রি স্পেস কি চেঞ্জ হয় স্যার?
As long as it's free space, no.
according to
Permittivity
medium.
of free space is the medium, is the free space a single medium, or is different medium in different places?
We part basically change sir. That's why K is changing.
Is the free space on a Shubhra, তোমার কোশ্চেনটা আরেকবার করো and listen to your question as you ask it. Take time. Slowly ask your question again and listen to your question as you ask it.
Yes sir, আমি বলছিলাম যে permittivity of free space তো চেঞ্জ হচ্ছে দেখে K এর ভ্যালুটাও চেঞ্জ হচ্ছে।
Permittivity of free space চেঞ্জ হচ্ছে না। Permittivity of free space is a constant number. Permittivity of plastic is a different number. Permittivity of glass is a different number. Permittivity of aluminum is a different number. Permittivity of iron is a different number.
Oh, acha.
Make sense?
Beautiful.
So the part that is covered over in this segment, have a look that it says that if Q1 and Q2 are similar charges, plus plus or minus minus, then they repel each other and F is positive. Try to think about it. If you use plus and plus, product is positive. If you use minus and minus, the product is also positive, which means whenever you are going to having a positive force, that force is supposed to be a repulsive force. Vice versa. If these two charges are opposite to each other, one is plus, the other is minus, which means plus minus or minus plus, they will attract each other. It means in that case, the product of these two numbers will be negative, which means F will have a negative value. This is the place where we talk that attractive forces are shown by a negative force, repulsive forces are shown by a positive force. This is exactly why the gravitational potential was an ever negative number. Because gravitational force on its own property will always try to bring objects closer, never further apart. So work will always go out of the system. Gravitational force will never try to separate out the particles. That's why gravitational potential was always a negative number. But for electric potential, we can have both positive and negative, because electric force can be repulsive, it can be also attractive. Either of them are possible. So we're going to see about these things over here. So we have over here a bit of a complicated calculation, which are a bit unlikely for your syllabus to show, but they might. That's why I usually make the kids understand this. This is very simple. But for those of you who are going to appear for the public examinations in Bangladesh, you are going to see this kind of maths quite a lot, even in your university admission procedure preparation. So it's a good read. Have a look. What we're trying to show over here, let's say we have two charges, Q1 and Q2, located at point A and point B, having their charges plus 4 Coulomb, minus 6 Coulomb. And they have a distance of in between distance of 50 centimeter. And then we have a test charge, small q. So we usually represent the field Keating charge with capital letter, and we represent the test charge or the force experiencing particle as low as small letters. So this test charge, small q, has a value of, let's say, plus 2 Coulomb. It is placed over here, where these two distances are 50 centimeter each, and this angle is 60 degrees as well. So this is basically supposed to be equilateral. It doesn't look like to be an equilateral, but it is supposed to be an equilateral. So because 50, 50, 50, and the particles are all placed in vacuum, so K has a value of this much. Now the question is asking you, determine the magnitude and direction of the force exerted on Q by Q1 and Q2. So what is the resultant force experienced by this charge because of these two? So we are not trying to find out how much force they exert onto each other, how much force this exert onto this one, or how much force this exert on this two. We are trying to find out how much force is experienced by this one because of these two. So let's go ahead and try this out. First, we can calculate. Because by looking at the signs of these two forces, we can understand that this Q is going to experience a repulsion force downward left, because they are both similar charges, whereas it's going to experience an attractive force in the upward right, because they are opposite charges. That's why these arrows are aimed in this direction. So we're going to find out the individual forces first. So considering Q1 and Q, the F1 represents the force available from the Q1 charge. F1 equals to 4 into 2 divided by 0.5 square into 8.99 into 10 to the power 9. So here the kid wrote it as Q1 Q divided by D square into K. So he wrote the K later, which is perfectly all right. So we calculate this force value. So this is the force that is working. So this is this force, this one. Then considering Q2 and Q, we calculate this force. This is minus, because the calculation gives us minus. Minus in this case would mean that this force is going to work away from the charge particle. This is working towards the charge particle. This is a repulsion force. Wow, thank you. টাকা লাগবে না? এটা তো টাকা বাকি আছে তাহলে। আচ্ছা, হ্যাঁ? হাতে লিখে আসো? ওকে, ঠিক আছে। Sorry. Hello? Acha. So F2 over here was calculated to be negative force, which is simply the plus or minus basically represent the direction of the force. So because we have already determined the directions over here by downward right or upward right, we don't have to bother about the plus or minus for the vector diagram. But remember these two directions. We can judge this direction simply by looking at the signs of these two charges. So over here, the F2 is coming to be this number. Now we have to go forward to draw a vector diagram, which is shown over here. Take a good look at this vector diagram. Coulomb, এই vector diagram বুঝা যাচ্ছে? একটু respond করো।
Sir, I don't get it.
Let's say
এটা resultant force টা না?
exactly. So let's say that our particle is over here. We are trying to find out the we're trying to find out the resultant of these two forces, F1 and over here F2. We're trying to find out the resultant of these two forces. So একটু wait করো. So what we're gonna do, we're gonna to be able to draw them by a triangle rule, we're gonna place these forces one after another. So that's what we are doing over here. This is F1, this is F2, they are placed one after another. So the resultant is gonna be like that. This figure is not representing the actual orientation of these two charges. Don't mess this up. This is the force vector triangle. Component force F1, component force F2, resultant force like this. So the resultant is gonna work upward right in this direction. So we're gonna trying to find out how much is this gonna be. So এখানে অনেক কিছু লেখা আছে, length of the diagonal same as the what is this, rhombus. আচ্ছা, length of এই diagonal কোথা থেকে আসলো সেটা আমি বলতেছি, just give me a moment. So one of the ways that we can work with this thing is how did this work? This is 50 50 50 theta r, then a bit of cosine rule, 60 degree downwards, 60 degree upwards. Oh, acha. হ্যাঁ বুঝছি. So what this kid did over here, he went for the division of the forces in their components. So what he did is this. He went. I mean, this is the triangle rule that I believe I drew on the board. So he copied this, but he preferably solved it by dividing the forces in components. So this is what he did over here. I'm gonna elaborate this figure. I understood what he did over here. So what I can show you for the elaboration is this is an axis system. Let me choose a bit thinner line. Let's say this is an axis system. I'm going to shift to my writing pad. And let's say this is another axis system. So let's put those two forces with their angle and with their direction. So let's say I'm going to show the forces with blue. Damn it. Okay. So let's say I'm going to show the forces with blue. So let's say I'm going to first show F1 over here. So F1 is going to be in this direction, where this angle is supposed to be how much? This angle is supposed to be 60. And the value of F1 is how much? 2.8762. So this is 2.87 or 2.88. This is 4.32. So this is going to have some length, but this will be the alignment. So let's say this is 2.88 in terms of length. And let's say the F2 is working upward right, where it is producing an angle of 60 degree with over here, which means essentially that if I try to the axis system over here, this angle should be also how much? 60 degree. So I can show the other forces with green straight line over here. This should be slightly bigger. Why slightly bigger? Why slightly bigger? Because the
force is bigger.
Exactly, because the magnitude is large. Okay, so let's say this is a scale diagram, although I did not measure, but I can very well confirm you that this angle is 60 degree and this angle is also 60 degree. So if you now have the two forces over here in terms of the parallelogram, so you can complete the rhombus over here, which is gonna be, it's not gonna be a rhombus, it's gonna be actually it's gonna be a what? It's gonna be a parallelogram. So we can complete the parallelogram. And the resultant, let's say I'm going to show it by purple, can be shown from here to here. So this is going to be a resultant. So this is the same math done in using parallelogram rule. So you can calculate using this as well. So what he did over here, he drew this figure. So he is trying to represent this figure over here by dividing the forces. Benefit of going for measuring these components in this manner is that you can individually calculate the components and then you can go for the resultant, which brings the procedure much too simpler. What I mean, I'm going to show you the calculation of this procedure in detail because I want you to appreciate and understand this, what is happening. This was our F2, this was our F1, this is our 60 degree, and this big angle is also 60 degree, and we do not know how much is this. So this angle is theta. We want to know how much is this, and we also want to know how much is this. Now this is the diagonal of a parallelogram. So you can calculate the value of this thing using the cosine rule formula. So that's what I did over here. That's the length of this value. And then if you want to calculate the angle, what he did over here, he went for the calculation by some sine ratio. So what he did, I believe, is that this is 120 degree. So how could he use that? This is 60 plus theta. This is 60. So I'm not sure how he did that. Can anybody tell me how he did that? Did he consider theta to? Oh, he considered theta to be here, which is supposed to be 30 degree. Why did he consider theta to be here? Not sure though. Okay, anyway, I'm going to show you my version of the calculation. Obtaining the magnitude is pretty simple. If you want to find out the angle, you can go for the traditional way, or the other way I can go. I mean, the whole point of drawing this figure, that's what I'm trying to get over here. The resultant force Fx, so summation of these forces, and let me use a bit more space here. Oops. Okay. So I can first find out the summation of these forces on the x-axis. So let's say I'm going to write summation of force in the x-axis should be equals to, considering towards right as positive. So towards right as positive, this should be F1 cos 60 plus F2 cos 60. And considering upward as positive, I can write summation of the vertical forces should be F2 sin 60 minus F1 sin 60. Minus কেন হচ্ছে এটা বুঝতেছো? বলো minus কেন? Because F1 is working downwards. So এখান থেকে তুমি একটা value পাবা, and once you get this value, finding out the theta is very simple. In that case, tan theta would be equals to sum of Fy divided by sum of Fx. এখান থেকে তুমি খুব easily theta by করে ফেলতে পারবা. So that's how I would do for the division of forces. So this is how we can find out the resultant on this force. So that's, I mean, there are many different ways to solve a vector problem. This is just one of the ways that I showed you, where that popped in my head at this time frame. Maybe if I took the class, let's say 1 month later, or for any other batch, I might show them in a different way. But point to be noted that, does this procedure make sense? I'll take questions now. Raise your hands and I'll take questions one by one. Don't just rush in the questions, preferably, please. Sajid, bolo.
স্যার আমার কোশ্চেন ছিল যে আপনি যে ভেক্টর ডায়াগ্রাম রাখছেন ওটা নিয়ে, ওই যে লেফট সাইডে নোট যে রাখা আছে,
বলো বুঝতেছি। হ্যাঁ,
ওখানে F2 যে সাইনটা, ওই F2 সাইনটা কি মানে নিচে ডাউনওয়ার্ড দেওয়া না উপরে দেওয়া, মানে F2 সাইনটাকে ভুল দেওয়া আছে নাকি? আমি এটা বুঝতে
না, F2 সাইনে ভুল দেওয়া নাই।
আচ্ছা,
F2 is the force experienced by small q because of the capital Q2. This is working upward, right? So if I give some elements over here for your understanding, let me zoom on here a little bit so I can draw easily. If I give you some alignment for understanding, I can give you that if this is a horizontal line and if this is a vertical line, this is 60 degree, this is also 60 degree. This length is supposed to be the F1 magnitude, this is supposed to be the F2 magnitude. So we have drawn the two forces with proper angles with each other. So essentially the in-between angle is supposed to be how much? 60 degree as well, right? Because, so that's why, so now we are having, so this is the resultant force that we're trying to find. So let's say this is our resultant. So I'm actually doing this R. So what I'm trying to show you is that R is supposed to be the vector sum of F1 plus F2. So that's the triangle rule. F1 and F2 are placed in the same sequence, resultant is obtained in the opposite sequence.
আরেকটা কোশ্চেন আছে ওই ডান দিকের ডায়াগ্রামটাতে।
Yes, বলো।
সো এখানে ওই যে F2 cos 60 যে দিছেন এই পার্টটা মানে এটা আমাকে একটু বুঝান, আমি ভুলে গেছি।
ওকে,
ওই F2 cos 60 মানে আমি বুঝতেছি না কোন লাইনটাতে গেছে।
F2 cos 60 মানে হচ্ছে এই 60 ডিগ্রির সাথে adjacent component. So what it means is F2 এই পার্ট এইটুকু হচ্ছে F2 cos 60.
আচ্ছা আচ্ছা বুঝছি, মানে বেসিক্যালি হরাইজন্টাল কম্পোনেন্টটা নিছে নাকি?
That's why I wrote X.
আচ্ছা 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 বুঝছি বুঝছি, ঠিক আছে, থ্যাংক ইউ।
Abiaz. Hello, Abiaz. Okay, Ornima, go ahead.
স্যার যে নোটসে যে ডায়াগ্রামটা দেওয়া না যে থিটা 51
এটা
ফোর্স ডায়াগ্রাম না তাই না?
কোনটা বুঝি নাই।
এই যে ডায়াগ্রামটা দেওয়া লেন্থ অফ ডায়াগোনাল সেম অ্যাজ রম্বাস যে
এটা
এটা তো ফোর্স ডায়াগ্রাম না না?
এটা সে কিসে বেসিসে আছে I'm not sure because Anas's brain works really efficiently. I think he went through some real good time warp level technology over here, but I'm not sure what he did over here, but the calculations are definitely correct. I have that much faith on him. I couldn't make sense of what this diagram is, that's why I elaborated my understanding of this diagram over here. That's the best way I can put, but I cannot make sense of this diagram. I cannot.
কিন্তু স্যার এটা তো ফোর্স ডায়াগ্রাম হবে না, কারণ এটা 50 দেওয়া আছে, এটা ডিসটেন্স না?
হ্যাঁ, এটা ফোর্স ডায়াগ্রাম হওয়ার কথা because he was আচ্ছা I think he logically tried to calculate out the angles, which was not essential because it was an equilateral triangle. Maybe if he drew this angle to measure the lengths, it was not I mean what this diagram shows, because he used the 50 over here, which means that he used the length information over here. So maybe he tried to figure out the in between angles. But to be honest, if I think from my perspective that those angles are actually known, the only involved angles over here can be 60 degree, 30 degree, or 90 degree in applicable cases. So maybe this figure is not at all very essential. But if you had different lengths, for example, let's say 50 over here, 40 over here, 45 over here, then you might require something like this to actually get the angles between those two things. Or in other words, I can tell you, this amount of information that is over here is redundantly available. You have the length information, you also have the angle information. If an actual question pops in your exam paper, you should not have access to all the information. They might only give you the angles and one of the length, or they might give all the 3 lengths and not give you the angles. So you might have to actually have to go through to calculate this process. Maybe that's what he attempted over here. বুঝতে পারছি?
Yes sir.
Abiaz.
Sir, can we assume that the charges Q1 and Q2 are stationary, like fixed in place?
We are trying to, I mean, this is the kinematics part of the math, which means we are assuming this is a certain state of the charged particles position at a certain time instant. We are trying to figure out what is the resultant force. How they're going to move afterwards is not being considered here. So for our mathematical procedure, we should assume, or we can assume, they are stationary for the ease of understanding, but they might not be stationary. They might be moving in a certain scenario, and this might be an instance of time where we wanted to do the calculation.
So it's just the instant for of the forces acting on the test charge Q.
Yeah, exactly. So
Thank you,
another way I can further elaborate your question is that try to think about the scenario for the solar system. Let's say there is sun, there is earth, and there is moon. Consider everything else is absent. Let's say the system that I'm trying to describe over here is consisted of sun, earth, and moon. Now, as the earth rotates around the sun, the moon also rotates around the moon. Sorry, the moon also rotates around the earth. Now, the individual forces, because of the gravitational pull of these 3 different things, is not a constant number over the duration of time. But if you want to calculate the force between each other, you have to freeze time at an instant, and at a certain orientation of these 3 objects, you can actually calculate the forces accurately. Do I make sense?
Yes, sir, because the force is a changing variable.
Exactly, because the distances are changing, because the shape of the Earth's orbit is not perfectly circular, and then the distance and the position of the moon is also going to be at some variable. So this can be a scenario like that as well. So we do not know whether the particles are moving or not. We are trying to find out the forces that is acting on Q at this instant because of Q1 and Q2. That's what we're trying to get at.
I get it, sir. So Q1, whether Q1 or Q2 are moving or not, it's not relevant.
It's not
This
relevant
case.
for this scope. Exactly. Yes. They might be moving, they might be stationary. But if you assume them to be stationary, the processing of the problem in our head can become a bit easier for us to we have less things to worry about.
Okay, sir, that makes sense.
Pardon?
স্যার আপনি যা লাইক বলেছিলেন যে কিউ টু হচ্ছে কি ফিল্ড ক্রিয়েটিং চার্জ, রাইট? সো স্যার আপনার অ্যারোটা স্যার কিউ টু থেকে স্মল কিউতে কেন যাচ্ছে না? Why Q to be like Q small Q থেকে বড় Q তে কেন যাচ্ছে Q2 তে?
Because have you read the question? Determine the magnitude and the direction of the force exerted on Q by Q1 and Q2. So we want to find out what is the force experienced by this one. This is going to pull this one downward right, and this is going to pull this one upward right. That's why I gave these forces.
No, মানে এটা কি কোশ্চেনে দাওয়াই আছে, মানে অ্যারোগুলো দাওয়াই থাকে?
কোশ্চেনে দাওয়া আছে। But if you
like আমাদের ডিটারমাইন করতে হবে না, তাই না, কোন দিকে অ্যারোগুলো যাচ্ছে?
But what you should also remember that Newton's third law is equally applicable for applicable cases, which means that Q is being pulled by Q2 in this direction. Vice versa, logically speaking, Q is also pulling Q2 towards this direction. But we are not trying to bother about what are the force experienced by Q. We are bothered about what is the force experienced by Q.
Okay, sir. Got it. Thank you.
Sure. Moving on to the next part of the lecture. So the next thing that we have over here is this. So I'll take this one out as well. Okay, so that I can access it from here very easily. Electric field strength. Have a read, everyone. Other than me starting to badgering your head with this one, have a read. পড়া হচ্ছে কি? নাকি পিডিএফ তে দেখাবো? আচ্ছা পিডিএফ তে দেখাই। পিডিএফ টা অ্যাকচুয়ালি ডাইনামিক্যালি জুম করা যায়।
জি স্যার।
যতটুকু পড়া যাচ্ছে ততটুকু পড়ো, তারপর আমি নিচে নামাই দেব। কোনো কোশ্চেন থাকলে আমাকে বলবা। এটুকু পর্যন্ত আগের জিনিস। এটুকু পর্যন্ত পড়ো। এই যে যেখানে মাউস রাখছি এই পর্যন্ত পড়ো, তারপর আমি নামাই দিচ্ছি।
স্যার
জি বলো।
স্যার ওই ম্যাক্স ডিসটেন্সের পয়েন্টটা বুঝি নাই।
কোনটা?
ম্যাক্স ডিসটেন্স, to maintain max distance between them due to repulsion.
আচ্ছা সেটা হচ্ছে let's say an object is negatively charged. I'm trying to use the idea of negatively charged because I can talk about electrons easily. Think about this. Let's say we have a metallic sphere. I'm using the example sphere because spheres are uniform to discuss about. If we consider a sphere that is negatively charged, let's say it now has 1 million extra electrons than its proton number. these extra electrons are going to produce a total charge onto the charge in the sphere. Now, this charge, how these charge particles or how these extra electrons are going to be located onto this metal sphere? Should they be clumped up at a location, or should they be spreading out, trying to spread out from each other?
They should spread out.
They should spread out because they are all like charges. So on the surface of the sphere, these extra electrons are going to try to arrange themselves in a manner so that they can maintain maximum in between distance from each other. As a result, none of these charged particles or none of these extra electrons would remain anywhere beneath the surface. Because try to think about it. I mean, if you have 1 million electrons on the surface, there is a average in between distance between each pair of electron. If they get, let's say, 1 centimeter inside the surface, that in between distance will become smaller, right?
Yes, sir.
That's not going to happen. That's what this means.
স্যার
So-
ওই পার্ট বুঝলাম না, স্মলার হবে কেন?
Try to visualize. Let's say you have a sphere of a certain radius, and there are 1 million particles equally spaced out onto the surface of the sphere. If the same sphere becomes somewhat smaller and you still have 1 million particles equally spaced on the surface, for which of these cases you would have smaller in between spaces between the surface particles?
স্যার smaller sphere has smaller space.
Exactly, but that's not supposed to happen because those electrons are like charges and they're going to repel each other. So they're going to try to maintain maximum in between distance. Hence, they would always locate themselves on the surface.
So, sir, basically, if we go inwards, the total surface area occupied by those electrons decreases,
Exactly.
and hence their distance between them.
Exactly, which is not naturally possible because naturally they repel each other.
Okay, sir. Thank you, sir.
মিথিলা বুঝছো?
হ্যাঁ স্যার বুঝছি।
ওকে, ফারদিন তুমি কি হাত উঠাইছো নাকি এটা আগেরটাই?
স্যার আগেরটাই নাও, সরি।
সমস্যা নেই।
তাহলে স্যার যদি তাহলে ওরা মানে ন্যাচারালি ডিসটেন্স মেইনটেইন করে থাকে, তাহলে স্মল অবজেক্টস গুলো কিভাবে ন্যাচারালি ডিস্ট্রিবিউটেড থাকে? আমি বুঝলাম না জিনিসটা।
তুই কোশ্চেনটা একবার বলো, আমি কোশ্চেনটা বুঝি নাই, স্লোলি একবার বলো।
মানে বেসিক্যালি যে বলতেছিল না, মুগ্ধ বলতেছিল না যে আপনার মানে ইলেকট্রনস গুলো হচ্ছে গিয়ে স্মল অবজেক্টের ভিতরে ওরা সারফেস এরিয়াটা কম থাকে, কিন্তু ন্যাচারালি তো ওটা হয় না।
Well, if an object is neutral, then there is equal number of protons and electrons within this object. So there is no resultant charge that exists within that object. So it doesn't produce an electric field around it. Or in other words, I can say the total positive field produced by the positive charges, nuclei, and the total negative field produced by the orbital electrons, they cancel out each other. So saying something doesn't exist is almost not, is exactly same as saying something that there's two equal things which balance out each other. I mean, think about it. If the resultant force on an object is 0, we can say that the object has no force acting on it, right? But that doesn't essentially mean it has to be exactly that. I mean, having an object having 0 resultant force is possible. Having an object experiencing no force at all is practically not possible because everything is part of the universe. Do I make sense? So, if an object is altogether positively charged, then it will produce a positive field around them. In that case, the total electric field produced by the nuclei is going to be stronger compared to the total negative field produced by the orbital electrons. So the positive field is going to be the exhibit output, which is going to be radially outwards, starting from the surface and go and continue outwards, and vice versa for negatively charged bodies. So the reason I'm bringing about the ideas of positive field and negative field is to give a comparable idea that the field is not essentially created by a single particle. The field is created by both the positive charges and the negative charges. The question is, which one has more effect? বুঝতে পারছি?
কিছুটা হ্যাঁ স্যার বুঝছি।
মানে হচ্ছে, try to think about it. Let's say an object has some positive charge within itself, nuclei. They are trying to produce an outward field, which I'm trying to name as a positive field, outward field lines. And the object also has orbital electrons. They are negatively charged, so they are trying to produce an inward field, because I'm trying to denote that as a negative field. If the total number of charges of positive and negative charges are exactly equal, these two fields are going to cancel each other, so there won't be any resultant field. The basic definition for a neutral object.
আচ্ছা বুঝছি আমার মনে হয় I get it what you're trying to say মানে বেসিক্যালি বলতে চাচ্ছেন যে মানে রেজাল্টেন্টটা প্রত্যেক সময় শো করতেছে তাই তো
Exactly.
আচ্ছা আচ্ছা বুঝছি
বুঝা গেছে মানে that's one way to visualize the whole thing to give us a better understanding of how the field actually works.
বেসিক্যালি আপনি বলতেছেন যে মানে নেগেটিভ থাকা মানে নেগেটিভ চার্জ থাকা মানে এই না যে এর মধ্যে পজিটিভ চার্জও নাই মানে পজিটিভ চার্জ আছে বাট নেগেটিভটা রেজাল্টেন্ট হিসেবে আসতেছে কারণ ওটা বেশি অ্যামাউন্ট আছে
Exactly that's what I said. Beautiful.
স্যার
Yes.
আমাদের যদি একটা স্ফিয়ার থাকে আর কয়েকটা চার্জ পার্টিকেল যদি সারফেসে থাকে আর বাকিগুলো যদি সেন্টারে থাকে তাহলে তো ওইগুলোর ভিতরে ডিসটেন্স মানে ম্যাক্সিমাম হয়ে যায় মানে রেডিয়াসের সমান হয়ে যায় তাহলে কেন ইনসাইডে যাবে না
Because whenever we consider the total charge, I mean, if you consider the total field produced by all the constituent charge particles of an object, I mean, there comes a much detailed understanding for you to understand. I mean, if I start from the very bottom, as far as our experience and our discoveries go, not inventions, discoveries go, quarks are the fundamental particles, which you have come to experience in your AS syllabus, right? Up quark, down quark.
Yes, sir.
Now, positive charges. So from that idea, each quark work as a source of positive charge. So each quark will produce a field around them. Then in a baryon particle, multiple quarks join together and produce a baryon. So if it is a positive baryon, then it's going to produce a resultant electric field from itself. That resultant electric field will be an exhibit property of the combined electric field of all of those three quarks, right?
Yes, sir.
Now, if you consider for a nucleus, in the nucleus you have multiple baryons. Let's say if you consider a very simple example of a helium nucleus, you have two protons. Neutrons are charged and neutrons are bad. So actually neutrons are bad keno. Neutrons are bad, you know why the neutrons don't have any charge, because inside the neutrons you have equal amount of positive and negative charge particles. So the positive electric field produced by the positive quarks are perfectly cancelled out by the negative electric field produced by the negative quarks. So it doesn't exhibit any resultant electric field around them. Whereas for the protons, they exhibit a resultant electric field around them because their positive field is more stronger compared to negative field. So if you consider for helium nucleus, a helium nucleus is going to exhibit an electric field that is the behavior output for a +2 charge. But if you consider for helium atom, distinguish the word helium nucleus, helium atom. So whenever I say helium atom, now you have two orbital electrons. These two orbital electrons will also produce the individual electric field. If you combine them up together, you're gonna get a collaboration, or you're gonna get a combined negative electric field. What happens for a neutral helium atom, the positive field produced by the nucleus is exactly equal in magnitude at any location around that nucleus by the negative field produced by the two electrons. As a result, it does not produce any resultant electric field around them. We say the object is neutral. And you can expand out this scaling factor further down the line. You can consider molecules, then you consider big objects, then you consider big planets, then you consider solar systems, universe, blah, blah, blah. বুঝতে পারছি?
হ্যাঁ স্যার এতটুকু বুঝছি কিন্তু আমি জানতে চাচ্ছিলাম যে চার্জ পার্টিকেল গুলা কেন স্ফিয়ারের ভিতর দিকে যাবে না কারণ যদি যায় তাহলে তো রেডিয়াসের মানে যত ডিসটেন্স তার তো সারফেস থেকে ডিসটেন্স বাড়তেছে আর রিপালশন তো ডিসটেন্স বাড়ানোর জন্যই ওরা করে
Now you are trying to figure this. You're trying to think in the wrong direction. I'm gonna point out the error in your description so you can pinpoint the understanding. সেটা হচ্ছে whenever I'm trying to give you a scenario where the charged particles are all located on the surface, so their repulsion is lateral, not inward. The resultant field by all of those charged particles is either radially outward or inward. But the in-between interaction of the charged particles, let's say electrons which are located on the surface, they are actually repelling each other laterally. Laterally means along the surface of the sphere. Does it make sense?
Yes, sir.
Now, if you push them in a smaller radius sphere, they have to get closer to each other. Right?
Yes, sir.
That's not going to happen because naturally they are repelling each other. This is why all the free electrons, they're always going to show up on the surface. This is why the metallic bond actually works. The reason metallic bond works, I mean, how does the metallic bond works? Before I get into the idea of metallic bond, let me just precisely ask you, did it make sense? The problem that you are having, that you are assuming that the force was being experienced towards the center. No, the electrons are not experiencing force towards the center because of each other. Electrons are experiencing force laterally or tangent to the surface of the sphere because of each other. They are trying to push each other out the farthest distance apart from each other because they are like charged particles. That's why they are trying to maintain a maximum in between distance. That's why they will prefer to show up on the surface rather than inside.
স্যার তার মানে সেন্টারের দিকে যাওয়ার তাদের কোনো প্রয়োজন নাই বিকজ কোনো ফোর্স নাই, রিপালশন ফোর্স।
You ask me the question once again slowly and listen to your question. I hope you will get the answer. Ask the question again and listen to your question.
Sir, question is that why aren't the like charges moving towards the center of the sphere for maximum distance?
Because like charges repel, and repulsion are going to try to separate them out, or repulsion will naturally try to make the in-between distance as big as possible.
আচ্ছা স্যার, বুঝতে পারছি।
Clear to say?
হ্যাঁ।
Beautiful. So the other additional part that I was trying to get is that the way metallic bond works is that any metal piece has a lot of delocalized electrons, which belong to the metal piece, but does not belong to any individual atom of that metal piece. So this brings us to the idea that whenever the electrons actually become free from their individual atoms, they prefer to go anywhere. Now, where would they go? Now there are two forces in into thing that once the electron becomes free of a certain metal atom, that metal atom becomes a positively charged ion, and the electron is a free delocalized electron. Because there are a huge number of free electrons, the electrons are going to repel each other and try to become as far as possible from each other, which is possible if they locate themselves on the surface. Hence, all the electrons show up on the surface. Now you might wonder, then why don't they leave from the surface? They cannot leave from the surface because as they leave from the individual atoms and make all the atoms into positively charged ions, that entire positively charged core start to attract the electrons as well, because now they are positively charged and the electrons are negatively charged. So because of the positive core, there is a total attraction of the entire electron layer towards the center of that metal piece. Consider the metal piece as a sphere. Let's say metal sphere. All the positively charged iron core is attracting the electrons. That's why the electrons are getting stuck onto the surface, but they don't want to get into the bolo.
Can you repeat this again?
From where?
From it cannot leave the surface.
The electrons cannot leave the surface because of the effect of two forces. I mean, why should the electrons be located at the surface? That's what I'm trying to get at. So try to understand two different forces in action here. One force is that the positively charged core that was created by the electrons leaving from the individual metal atoms. So you have a highly positively charged core which is trying to attract all the electron towards themselves. Then again, there are a lot of free electrons which are laterally repelling each other to maintain maximum distance in between them. So the electrons themselves are trying to spread them out by repelling each other, and the positively charged core is trying to attract all the electrons because they are positively charged and they want to get those electrons back. These two forces equilibrium out, and as a result, electrons are located on the surface. This is why all the very thin electron layer, very thin because electrons are extremely small, but they are very large in number. Very thin electron layer that exists on the surface of a metal piece, which continuously keeps squashing onto the metal piece. It's a very strong compressive force from that layer of electron onto the positively charged ions. They exist on the surface because they repel each other laterally, and they're attracted inwards because they are negatively charged and the core is positively charged. Because of this compressive force, metals can be so strong. And this is also one of the explanation, not entirely, one of the explanation that why aluminum is considered to be such a good material. Because each aluminum atom gives out free electrons into their lattice. Each copper gives out only 2. Each sodium gives out only 1. So sodium can be cut like a butter. Copper can be very easily bent by hand, but aluminum with appropriate dimension can be extremely strong because that compressive force from that electron layer onto the core is extremely strong.
তার মানে ইলেকট্রোস্ট্যাটিক বন্ডিং যত স্ট্রং তত হচ্ছে মেটালটাও স্ট্রং।
This is one of the factors. There are more factors to this. The orientation of those positively charged ions. For example, you can have rhombohedral orientation. You can have chatusthaloke English key. What is the structure of carbon atoms in a diamond? Tetrahedral. You can have tetrahedral, you can have rhombohedral, you can have pyramidal. There are a lot of different orientation things. That also plays a very significant role for the strength of the metal. And there is another factor is the radius or size of the atom. That also plays a very important role as well. But these are other stuff that I'm not getting into. This is essentially a part of metallurgy. I am trying to get you the idea about the effect of the actual charges of those particles. But could I transfer my idea?
I understand, sir.
Sir, so basically, as all the electrons are at the surface, there is no charge inside, right?
There is?
Like, there is no charge inside the sphere.
There
Electric
is.
field নাই কোনো।
That's the point that I was trying to make through the entire case. If you consider each individual atom or quark or nucleus as an individual entity, there is charge, there is electric field. But whenever you are trying to consider the entire object as a single thing, we're going to talk about the resultant field produced by this thing. If a metal has equal number of protons and electrons, then there is no charge of this thing. But if let's say if a metal piece is positively charged, then the positive charges are physically located at the center of the nucleus, which is in the core of the ion. So electrons will be still located on the surface, and the electric field around that sphere would be available outwards, not on the inside. So it would be a much more easier for you to understand that if you consider a hollow sphere, try to visualize that. Consider a hollow sphere. Can you visualize a hollow sphere?
Yeah.
Consider a hollow sphere. If you have a hollow sphere made up of metal of uniform thickness, let's assume, in that case, all the free electrons are be located on the outer surface because, like I said, they are trying to maximize the in-between distance. Would you have any free electron available on the inside surface? Would you have any free electrons available on the inside surface? Would you? Hello?
না স্যার
স্যার শোনা যাচ্ছে না?
না তো এই যে শোনা যাচ্ছে না শুনছি, তো এর আগে কি কিছু শুনি নাই। I asked that.
বলছি।
আচ্ছা, okay. So there wouldn't be any free electrons available on the inside surface. All the free electrons will be located on the top surface. That's why the electric field would be starting or finishing. Starting or finishing actually means outward or inward, the direction of the field lines. That's why the electric field will be existing only outside the metal sphere. No electric field would be available inside the electric sphere, considering the entire object as a single entity.
এই পার্টটা একটু কনফিউজড হয়ে গেলাম, আরেকবার একটু বলেন তো
স্যার একটু সামারি করে বলবেন এই পার্টটা, মানে পুরো জিনিসটা।
সামারি হচ্ছে এইটা, এইটুক পড়ো, এইটুক যদি বোঝা যায় তাহলে আর কোনো ঝামেলা নাই।
স্যার লাস্টের লাইনটা শুধু বুঝি নাই, ইনসাইড আ চার্জ বডি देयर ইজ নো চার্জ, ওই পার্টটা শুধু বুঝি নাই, বাকিটা বুঝছি।
এটার আইডিয়াটা হচ্ছে whether an object is positively charged or negatively charged, we are gonna consider those charges to be physically present exclusively on the surface of the object.
মানে স্যার পজিটিভ চার্জকে নরমালি ইনসাইডে কনসিডার করার কথা কিন্তু ওরা বাইরে কনসিডার করতেছে এরকম
Because we are considering the whole thing as a single entity.
তো স্যার ইলেকট্রিক ফিল্ড লাইনটা আচ্ছা মানে বেসিক্যালি পজিটিভলি চার্জ যদি হয় পার্টিকেল তাহলে রেজাল্টেন্ট পজিটিভ টু নেগেটিভ আর একটা নেগেটিভ চার্জ টাইমকে এরকম the field line is going to the negative charge.
Shubhra, I think you are doing monologue, so I couldn't catch the question.
Yeah, sir. মানে আমি বলতে চাচ্ছি স্যার যে পজিটিভলি চার্জ মানে রেজাল্টেন্ট যে ফোর্সটা পজিটিভ চার্জ থেকে না if a particle is positively charged sir তাহলে তো রেজাল্টেন্ট হচ্ছে পজিটিভ হচ্ছে না
Go ahead.
সো সারফেস থেকে স্যার হচ্ছে একটা পজিটিভলি চার্জ পার্টিকেলের সারফেস থেকে আরেকটা নেগেটিভলি চার্জ পার্টিকেলের সারফেসে অ্যাট্রাক্টেড হচ্ছে বা ফিল্ড লাইনস গুলো যাচ্ছে
Okay.
বাট স্যার তখন আমরা একেবারে সেন্টারটাকে মানে মানে এটা কি একটা আইডিয়াল কেস অর সামথিং
Exactly. Exactly. It's an ideal case. That's why I forgot to use the word ideal. Thank you very much for reminding this word. That I'm using. I was blabbering around this idea of ideal. I was saying that if we consider the entire thing as a single object, as a single entity, the total effect of the electric field would be shown that way.
স্যার ম্যাক্সিমাম ডিসটেন্স
তোমাদের খুব সিম্পল একটা জিনিস বলি মনে করো তুমি একটা সার্টেন একটা কম্পোজিট একটা বল ক্রিয়েট করছো যে বলের একটা একটা স্ফিয়ার ক্রিয়েট করছো যেখানে অনেকগুলো ছোট 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 পাথর আছে সবগুলো পাথরের সাথে সাথে একটা করে স্প্রিং দিয়ে ট্রায়াঙ্গুলার স্প্রিং দিয়ে একটা বল বানাইছো ঠিক আছে তুমি এটাকে স্কোয়াশ করো যতক্ষণ ফোর্স দিয়ে স্কোয়াশ করে রাখো ততক্ষণ স্কোয়াশ থাকবে the moment you let go of it all the springs are going to come back to the original state right why is that going to happen because the springs are going to try to expand out to their original state that's basically is what is happening to the electrons they are repelling each other that's why they are trying to maintain maximum distance in between each other which is possible to achieve at the surface I don't know a better set of words to explain this
স্যার বুঝে মানে চার্জটা হচ্ছে এক্সপ্যান্ড করে সারফেসে চলে আসে তাই বডির ভিতরে কোনো চার্জ থাকে না
beautiful
Sir, I have one doubt involving this concept.
Bolo.
Like, does the assumption of the particle charges as particles, does that still apply?
Yes. That's why these distances are always measured from center to center.
Still applies even though the electric field starts on the surface.
Exactly. So how this is going to affect our graph, we're going to see them in a bit. For the time being, even if an object is represented as a sphere, assume that this object has a charge of Q, which might be distributed on its surface evenly, but we are considering it to be a particle which is holding all of its charge concentrated at its center. Basically, a similar conversion like an object and its center of gravity for mass.
Sir?
Abhias বুঝছো হ্যাঁ ফারদিন বলো
স্যার আরেকটা জিনিস স্যার মানে আমরা we're assuming যে লাইক ইলেকট্রিক ফিল্ড লাইনস তো স্যার আপনার সারফেস থেকে যাচ্ছে রাইট বাট ইনিশিয়ালি তো স্যার আপনার সেন্টার থেকে বের হয় রাইট অ্যাজ শুভ্র সেড তার রেজাল্টেন্ট যদি পজিটিভ হয় আপনার নিউক্লিয়াস যে পজিটিভলি চার্জ ওখান থেকে আপনার হচ্ছে নেগেটিভ চার্জ যায় টু দ্য সারফেস হ্যালো
হ্যাঁ আমরা তো এখানে আইডিয়াল কেস কনসিডার করছি না সো নিউক্লিয়াসকে আমরা আসলে কনসিডার করতেছি না এখানে আই গেস আমরা সব চার্জকে সারফেস
idea of nucleus and quarks to give you a much detailed version of the how the fields are created for individual particles but once we consider the entire object as a single thing, we assume that the field is produced by the whole thing as a single charged body. Generalize.
And from the surface. So.
And it will be producing its electric field from the surface outwards.
Okay, sir, got it. Thank you.
So let's have a look at this part over here. We have field creating charge that is capital Q. We have a test charge that is small q. They are spaced out at r distances from each other. So typically, this is the typical scenario that we go by. Small q is considered to be the charge particle which can move around, and capital Q is can be considered to be the charge particle which is stationary, and we'll be judging different aspect of this scenario. So if you consider the electric field produced by Q, this charge located over here, that can be produced by F by Q, because the definition of electric field strength is given by force experienced by unit charge. So if you consider this is our field creating charge, which we are considering for this scenario, the force that this charge exerts onto this one is F at this position. at this position. So F is the force exerted onto this particle, and at this position the charge on which this force is working because of this one is Q. So the electric field strength at this point coming from this object is F by Q. This Q is the charge that is located at the position where you are trying to measure the field strength, and that field strength is created due to the field creating charge. This is given by this one. So EQ equals to F by Q. So F is going to be given over here as KQQ by R square. Q and Q crosses out each other, and as a result, we can get KQ by R square. This is a basic equation for electric field strength. And vice versa, for example, let's say if we try to find out the electric field strength because of small q at position A, that would be E small q, or electric field strength produced by the small q charge equals to KQ by R square. Ekhane small q asche keno? Because if we try to find out the electric field strength produced by small q at position A, we have to divide the same force. The force should be same for each other, because that is Newton's third law. They cannot exert different force onto each other. They are going to exert exactly equal force onto each other. To measure the electric field strength produced by small q at position A, we have to divide the experienced force by this charge by its own force, by its own charge. So F by capital Q korle expression ta asbe. So electric field strength can be equally applicable for either cases. This is a very small but very important topic which might be useful for some mathematical calculation. Sheta amra worksheet korar shomoy bolbo. But this is the primary equation for electric field strength, which is given by KQ by R square, where K is the permittivity of free space, or that medium, whatever that medium is. Q is the field creating charge. R is the distance from the center of the field creating charge to that point. Or in other words, I can say, let me finish. In other words, I can say, I'll take a question. In other words, I can say that from a charged object of Q value, the electric field strength at a distance R from its center is given by this expression. This means how much force would this charged particle exert on 1 Coulomb charge at this position. So Q Coulomb charge experiences F force, 1 Coulomb charge experiences F by Q force. That's basically the definition of electric field strength, force experienced by unit charge, F by Q. Bolo, Sajid.
Sir, আমরা AS এর যে ফর্মুলাটা ওটা ইউজ করতে পাবো না কেন?
করলাম তো, E equals to F by Q তে করলাম।
না মানে বলছি যে এই যে F টাকে কেন সাবস্টিটিউট করতেছেন না পরে আবার ওই আগের ফর্মুলাটা দিয়ে আপনি যে আগে F equals to
সাবস্টিটিউট কেন করলাম? That's your question.
হ্যাঁ
Because this is being taught now, which was not taught in AS level. This is the additional part that you have to learn for your A2 syllabus. Let's have a look for electric potential. এখানে গাদাখানি ডেফিনেশন আছে, এই বন্ধ একটু পড়ো সবাই, এই বন্ধ একটু পড়ো, নিচের লাইনটা পড়ে, এই নিচের লাইনটা পড়ে, এই বন্ধ পড়ে আসো। The definition is very much similar like gravitational potential, only in this case the field is electric field. All right, I'll take over. So the way we are discussing this part is that for the sake of simplicity, we're gonna bring about the different changes over here later on. The way we are saying that, the way we define potential, that the amount of work that needs to be done to bring a unit in positive charge from infinite distance into a position of the electric field is the work done to, is the potential of this point. So we are talking about the work that is done to make this much movement, not this way. So the direction of movement that we're talking about from infinite towards the positive charge. So let's say that our test charge is plus Q, and this was initially located at infinite distance. Now we are trying to move this object at r distance from over here. So this is the position where we want to measure the potential. And just to measure the potential, we have moved this small plus Q charge by a minuscule distance dr in this direction. Dr represents differential distance, which means it is very small. I mean, dr is basically 0, but it's not entirely 0. So it's approaching 0, limit thing, infinitesimal. And because this is such a small distance, we are assuming that the force is remaining constant for this much distance. So external work means if we want to bring the object, bring the plus Q charge, test charge from the infinite distance to this position, these two charges are going to repel each other because they are both positive charge by our description. So if we want to move this test charge from here towards the left, we have to push from an external source to bring the test charge closer to the plus Q. To achieve this, we have to do some external work. That's why. And so external work done on Q to move towards plus Q by dr is dw equals to f into minus dr. এখানে আমরা মাইনাস দেওয়ার কারণ হচ্ছে this f is gonna be replaced pretty soon by the kqq by r square. This f does not represent the external force. This f represents what? The existing force within the system. What is the existing force within the system? It's the repulsion force between these two charge particles. So onto this charge particle, the test charge, what is the direction of this f force? Towards right or towards left?
Towards right.
The force experienced by the test charge because of this force, because of this charge, because of the field creating charge, is towards right. But we are trying to move it to the left. So because we are moving against the direction, so the angle between them is 180 degree, cos 180 degree মানে হচ্ছে -1. That's one way. Or we can simply write dw equals to f into minus dr, because f in direction is to the right, displacement direction is to the left, so that's why minus. So this minus sign is very important because it's going to come important for derivation later on. So this f is the existing force within the field, and dr is the displacement made in the opposite direction of this force. That's why there is a minus. Now we're going to integrate this with the appropriate range, work done to bring plus Q from r equals to infinite to r equals to r. So we are trying to integrate the amount of work done, how much work needs to be done to move it from here to here. So this is our initial case, this is our final case. So initial case goes at the lower limit, final case goes at the top limit. So initially there was 0 work done. Whenever we're going to move it over here, we're going to have W work done. So work is being integrated from 0 to W, and the distance or R over here should be from infinite to R. So we are doing the integration over here. You guys are awesome at integration. Indefinite integration করলে আমাদের constant আসতো, যেহেতু এখানে লিমিট দিয়ে দিয়েছে ওজন্য constant আসবে না। সো আলটিমেটলি সব হিসাব করে দেখা গেল যে এখানে আমাদের, আচ্ছা এখানে আমি যে প্লাস মাইনাস একটা ঝামেলা করছিলাম, এই মাইনাসটা আমাদের ইকুয়েশনে পরে ইনকর্পোরেট করছি আমি, ওই জন্য এখানে কিছু কাটাকাটি হয়েছে, বাট থিংস আর প্রিটি ভিজিবল. What you can see, there was a default minus sign over here. Integration ultimately gives us another minus sign over here. If we do multiply them, we get W equals to KQQ by R, which means this is the amount of work that needs to be done to move this test charge from infinite distance at a distance R from the field creating charge. Therefore, potential is defined as work done on unit positive charge. So we have to divide that work done by Q. So V equals to W by Q. This is the very basic definition of potential. So V equals to W by Q. So W এর ভ্যালুটা বসাই দিলাম, নিচে হচ্ছে Q, ওই QQ কাটাকাটি গেল, so V equals to KQ by R. This is the basic equation for voltage calculation for any charged particle. Or in other words, I can say the electric potential of a charged particle has a value of Q at a distance R from its center is given by this expression. One thing you need to understand is that potential is a scalar quantity. Work done by charge. Work is a scalar quantity, charge is also a scalar quantity, so potential is also a scalar quantity. But electric field strength is a vector quantity, because field strength is given by force per charge. Force is a vector quantity, charge is a scalar quantity. If you do the division, you still have the direction part left. Hence, field strength is a vector quantity. It is equally applicable in the gravitational chapter as well. Gravitational field strength is a vector quantity, whereas gravitational potential is a scalar quantity. Similarly applicable, not same but similar. So V equals to KQ by R. এখানে R ইনফরমেশন লেখা আছে রিলেশন বিটুইন E and Q. এটা Q হবে না, এটা হবে V. আমার মনে বোর্ডে লেখা ভুল ছিল। রিলেশন বিটুইন E and V হচ্ছে E equals to minus dV by dr. If you wonder where does this come from, this is actually pretty simple. V equals to what? আমি এখানে একটু লিখি। আচ্ছা, এখানে এই পেজটা আনি নাই আমি। What is, বলো দেখো, what is the expression for V? V equals to হচ্ছে V equals to হচ্ছে KQ by R equals to হচ্ছে KQ by R square. If I do dV by dr, if I differentiate this equation with respect to R, what am I gonna get? বলো। বলবান ডিফারেন্সিয়েট করে এটা বলো কি হবে?
KQ by R square
মাইনাস আসবে না একটা সামনে?
হ্যাঁ 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 আচ্ছা
এই যে দেখো
হ্যাঁ মাইনাস থাকবে
সেম জিনিস, which means minus E, or in other words I can write E equals to minus dV by dr. মাইনাসটাকে এখানে ব্র্যাকেটে দিতে হচ্ছে আমাদের calculation সুবিধার জন্য. We have to talk about the minus whenever we are working with graphs, but if you want to go for magnitude calculation, for any case for mathematical calculation, we can simply differentiate this thing and we can get the value. What this essentially means, this is a very significant term. Have a look. If you ever have a graph of potential versus R, এই গ্রাফের যে গ্রেডিয়েন্ট হবে
এনার্জি
ওইটাই হবে হচ্ছে ইলেকট্রিক ফিল্ড স্ট্রেংথ, বাট সামনে একটা মাইনাস থাকবে। So if you plot the negative gradient of this graph onto another graph, that will be a potential versus R graph. এই ইনফরমেশনটা বোঝা যাচ্ছে কিনা?
স্যার আরেকবার একটু বলবেন।
দেখো আমি যেগুলো লিখছি সেগুলো খেয়াল করো, বোঝার চেষ্টা করো। Have a look at the writing, then I'll explain, no big deal, but try to understand the writing.
স্যার ভোল্টেজ ভার্সেস
আমি একটা সিম্পল एग्जांपल বলি। মনে করো হচ্ছে ভিটি গ্রাফের গ্রেডিয়েন্ট হচ্ছে কি অ্যাক্সেলারেশন না? আর তুমি যদি ভিটি গ্রাফের গ্রেডিয়েন্টকে টাইম এক্সিস এর সাথে আবার প্লট করো তাহলে কি পাবা? অ্যাক্সেলারেশন ভার্সেস টাইম গ্রাফ পাবা না? পাবা কিনা?
হ্যাঁ স্যার।
তো সিমিলারলি ভোল্টেজ ভার্সেস ডিসটেন্স গ্রাফের গ্রেডিয়েন্টকে তুমি যদি আবার ডিসটেন্সের সাথে এগেইনস্টে প্লট করো, তুমি সেই কেসে ইলেকট্রিক ফিল্ড স্ট্রেংথ পেয়ে যাবা, বাট তার সামনে একটা মাইনাস থাকতে হবে। তার মানে হচ্ছে এটার গ্রেডিয়েন্ট যদি পজিটিভ হয়, যে সকল জায়গাতে এটার গ্রেডিয়েন্ট যে এই লাইনে যদি এরকম হয়, তাহলে এই ফিল্ড স্ট্রেংথ হবে হচ্ছে এই দিকে on the lower side, because a positive gradient for the VR graph will give you a negative potential. A negative gradient of the VR graph, a positive gradient of the VR graph will give you a positive electric field strength. So তোমার আমি ভুল লাগছে অ্যাকচুয়ালি, ভুল লাগছে সরি, এরকম যদি হয় মানে it's the gradient calculation. I messed up this thing. Let me just do control Z. And yes. So positive gradient of the VR graph will give you a negative potential. Negative gradient of the VR graph will give you a positive potential. এটা ইমপ্লিকেশনটা কি সেটা আমি গ্রাফ করানোর সময় আরো ডিটেইলসে বুঝাবো। ফর দ্যাট আমি এটা যেখানে বলছি এটুকু মাথায় রাখো।
স্যার
What is the gradient of electric field R graph?
Exactly.
স্যার
হ্যাঁ বলো।
আমরা তো আসলে ফোর্সকে উইথ রেসপেক্ট টু আর হচ্ছে ডিফারেন্সিয়েট ইন্টিগ্রেট করছি স্যার, রাইট?
That's what I showed, yes.
স্যার
তোমার কোশ্চেনটা কি শুভ্র?
স্যার মানে আমি পুরো জিনিসটা বুঝতে পারছি না, কি এই কারণে জিজ্ঞেস করছিলাম।
ও
উইথ
শিওর,
রেসপেক্ট
বলো।
স্যার এখানে ইন্টিগ্রেশনের মধ্যে কি আমরা ডিআর কে 1 ধরছি?
না, ইন্ডিকেশনের মধ্যে আমরা কোনো কিছু ওয়ান ধরতেছি না।
তাহলে ডিআরটা স্যার ওটা যে ইনভলভড হয় না?
মানে
স্যার ইন্টিগ্রেশনে তো ডিআরটার কোনো ইনভলভমেন্ট নাই নেক্সট স্টেপে, তো ওটাকে ওয়ান ধরছি কিনা সেটা জিজ্ঞেস করলাম।
কি বলো, 1/r² হচ্ছে আমাদের ভ্যারিয়েবল।
তো ওইটার যে
এই
পাশে
এই ভ্যারিয়েবল
ইন্টিগ্রেশনে তো ডিআর
Hold up.
থাকবেই।
তুমি চিন্তা করে বলো কি বলতেছো। ইউ নো দিস থিং বাট ইউ আর লুজিং ইনফরমেশন। ইন্টিগ্রেশন করার জন্য তোমার যে ভ্যারিয়েবলটা নিয়ে তুমি কাজ করছো সেটা একটা ডিফারেন্সিয়েট ফর্ম থাকবে না। এটাকে যদি ওয়ান ধরে ফেলি তাহলে তো আমি এটাকে কিসে গেছি ইন্টিগ্রেশন করব। ইন্টিগ্রেশন করার জন্য তো আমার ডিআর লাগবে না।
আচ্ছা স্যার, ওই জায়গাটায় আমি এর আগেও কনফিউজ করছিলাম। আর স্যার আরেকটা কোয়েশ্চেন ছিল, সেটা হচ্ছে আমরা যখন ওটাকে মানে একটা অবজেক্টকে ফোর্স দিয়ে ডিআর ডিসটেন্স মুভ করছি, তো সেই ফোর্সটা তো আমাদের ফিল্ড ক্রিয়েটিং মাসের অপোজিটে করছি, তাহলে এফটা নেগেটিভ হবে না?
এই এফটা এক্সটার্নাল ফোর্স না, এই এফটা হচ্ছে ফিল্ডের ফোর্স।
আচ্ছা স্যার, আর ডিআর তো ডিসপ্লেসমেন্ট নট ডিসটেন্স।
এক্স্যাক্টলি, ডেফিনেটলি।
কিন্তু স্যার ফিল্ডের ফোর্স কেন? কারণ ওয়ার্ক ডান না, ফোর্স অ্যাপ্লাইড এন্ড ডিসপ্লেসমেন্ট মানে ট্রাভেলড।
So in this case, we are trying to calculate that how much work is done by the force available from the system itself, or how much work the electric field is doing on the charged particle. I mean, I'm just mathematically believe that external work done would be positive, whereas the work done by the force available from the electric field would be negative.
বেসিক্যালি তাহলে রিপালশনটা আমরা ক্যালকুলেট করছি।
রিপালশনের এগেইনস্টে কতটুকু ওয়ার্ক ডান করতে হচ্ছে সেটা ক্যালকুলেট করতেছে। Or because I gave a minus sign over here, I can also say that we are calculating how much work was done by the repulsion. The amount of work that was done by the repulsion would be a negative value because work was done against the repulsion.
হ্যাঁ স্যার বুঝেছি।
আর স্যার নেগেটিভ সাইনটা দিই বিকজ হচ্ছে এটা যদি নেগেটিভ হয় তাহলে হচ্ছে ফোর্স নেগেটিভ মানে হচ্ছে আমার এটা
Can
পজিটিভ।
I help you? There is one more. রাফিদ বলো।
স্যার আমি বললাম যে দিস ওয়ার্ক ডান ওয়াজ ফর আ পজিটিভ চার্জ, তো সেক্ষেত্রে আমরা যদি নেগেটিভ পাই এটাকে আমরা পজিটিভ বানানোর জন্য ইউজিং আ মাইনাস সাইন, আর যদি এটা নেগেটিভ হতো চার্জটা তখন তো আমরা তাহলে নেগেটিভ বানানোর জন্য তখন মাইনাসটা ইউজ করতাম, রাইট?
No, let me put it this way.
আই মিন স্যার তখন ওয়ার্ক ডানটা নেগেটিভ হবে না ইফ মাই চার্জ ইজ নেগেটিভ?
Yes.
হ্যাঁ, তখন তো আমি এটাকে করলে ডিফারেন্সিয়েট করলে আই উইল গেট আ পজিটিভ ভ্যালু। সো সেক্ষেত্রে স্যার
বলতেছি, I'm giving you the implication. They have a look. This voltage equation through this generalized equation came to be kq by r. এখানে কোনো minus sign নাই, right? There's no minus sign, which means for a positively charged particle, the potential will be positive. If you place a negatively charged particle, if your source is a negatively charged particle, that's over here, your test charge is still positive because you have to use the test charge to be positive because potential was defined for positive charged particle. You can make this variable for individual cases, but you cannot make this one variable. That's the important bit, which means if you have a negative charge as your field creating charge, simply your potential would be negative because your kq would be negative, so your v would be negative, which would mean it's the actual charge object is a negative charge. So any potential created by any negative charge around it would be a negative and vice versa. এটা আমি তোমাকে কনভিন্স করতেছি, জাস্ট গিভ মি আ মোমেন্ট। ইন্ডিভিজুয়াল গ্রাফগুলো যদি আমরা জাস্ট করি, ইন্ডিভিজুয়াল একটা কিছু গ্রাফ দেখালে তুমি আরো ভালো বুঝবা। কম্বিনেশন গ্রাফ আগে দেখাবো। আচ্ছা, আগে ইন্ডিভিজুয়াল গ্রাফ দেখেন। ইন্ডিভিজুয়াল গ্রাফ আমাদের এই লেকচারে সামহাউ নাই। For a positive charge, the electric potential graph looks like this. if you have a spherical object, okay, the electric field strength spikes up at the surface because there's no electric field strength there because there's no charge. So it goes on like this. It starts exactly from the surface. Inside there is no charge, inside there is no electric field, there is no electric field strength. For potential, it is going to be like that. This is a KQ by R square graph. This is a KQ by R graph. That's why it's a bit more close to the point. This is a bit more further apart. That's one thing. And if you have the same thing for a negatively charged particle, have a look over here. Have a look over here. No, not this one. Okay, let me choose a different one. AJ. This is the part that I was saying. If you have your V versus R graph that has a shape like this, Rafi, তুমি কি এটা জিজ্ঞেস করছিলা?
Yes, sir. It is used for salam.
Acha. If you have a V versus R graph, where you have a shape like this, so what you can say that this voltage graph is altogether on the positive voltage axis, which means the actual charge which is producing this VR graph has to be a positively charged object. First of all, and then as we are slowly getting further away from the object, the potential is slowly becoming less. So it is decreasing, but it's always remaining positive because the original object was positive. For this object, the electric field strength is going to have a shape like this. Have a look. This is like this, and this is like this because E equals to minus dV by R. So the way your gradient is changing, that exact value plotting would give you the electric field strength changing. Once again, this exists on the positive side because have a look. The gradient of this entire graph is what? Negative, na?
Yes, sir. Negative.
More negative, less negative, less negative, less negative, less negative, which means more positive number, less negative, less positive, less positive, less positive, less positive number. So we're basically plotting the negative gradient of each of these locations over here, which is giving us the electric potential.
So sir, electric potential actually
hold up. একজন করে রাফিদ বুঝা গেছে?
জি স্যার, I got it.
আর তোমার কোশ্চেন আনসার পাইছো?
হ্যাঁ স্যার, আমি এটাই জিজ্ঞেস করছিলাম, আমি একটু গ্রাফটা নিয়ে কনফিউজ ছিলাম।
ওকে, আমি গ্রাফটা তখন দেখাই না, সো গ্রাফ দেখালে ইজিলি ক্লিয়ার হয়ে যায়। হ্যাঁ বল, শুভ বলো।
So sir, electric potential is actually decreasing with increasing radius.
Yes, KQ by R square. As your denominator becomes larger, your value becomes smaller. এই যে ইলেকট্রিক ফিল্ড স্ট্রেংথের ফর্মুলা দেখো। ইলেকট্রিক ফিল্ড স্ট্রেংথের ফর্মুলা কি ছিল? ইলেকট্রিক ফিল্ড স্ট্রেংথের ফর্মুলা হচ্ছে KQ by R square. এই যে এটা, which means if K is a constant, a vacuum, Q is your field creating charge, which is also considered a constant. So further you go, your R becomes bigger, so your electric field strength becomes smaller.
Y equals 1 by x square.
Exactly. সো এই পর্যন্ত থাকুক, আমি নেক্সট ক্লাসে বাকি জিনিসগুলো বুঝাবো।
স্যার আমার একটা কোশ্চেন ছিল।
বলো।
স্যার যদি v নেগেটিভ আসে তাহলে তো পুরো গ্রাফটা শিফট হয়ে যাবে না নেগেটিভ দিকে? লাইক জাস্ট
এরকম
হবে না?
এটা পসিবল হচ্ছে নেগেটিভ চার্জ অবজেক্টের জন্য। এন্ড এইখানে গ্রেডিয়েন্ট হচ্ছে হাই পজিটিভ, রাইট?
হ্যাঁ।
এখানে গ্রেডিয়েন্ট হচ্ছে লো পজিটিভ, এখানে গ্রেডিয়েন্ট হচ্ছে আরো লো পজিটিভ। সেগুলো সবগুলোকে উল্টায় দাও। সো এই কেসে ইয়ার গ্রাফটা হবে হচ্ছে এরকম।
বেসিক্যালি দুটো সিমিলার শেপই হবে।
সিমিলার শেপ হবে বাট সেম না। দিস ইজ 1 by R or some version of 1 by R. This is some version of 1 by R square. That's the basic thing. বুঝা গেছে?
জি স্যার।
Kids, thank you very much for your attention. We're going to continue this lecture next class, and then we're going to slowly go further down the line. Okay, I'm stopping the recording. Fahim aso? Na chole gaso?